בוקר טוב לכולם. אני כבר לצערי שנה וחצי לא עובד ב-Node.js, אז לא היה לי משהו חכם להגיד, אבל בכל זאת הגשתי את ההרצאה הזאת, כי שנה שעברה נתתי הרצאה על ESM Loaders, ו-ESM Loaders עובדים בתוך Worker Threads, אז למדתי את הנושא של Worker Threads, אז אמרתי, יאללה, יש כל כך הרבה דברים מעניינים לדבר עליהם בנושא של Worker Threads, אז יאללה. וזה נכון שבקינוט הוא דיבר קצת על Worker Threads, אבל הוא דיבר 5 דקות ואני הולך לדבר חצי שעה. אז יאללה, אז אל תאמינו לשמועות. Oh, wait, I should skip to English. Sorry about that. Don't believe the rumors. JavaScript really is multi-threaded. So yeah, I go all the way back to the 90s. I have 35 years of experience. Never been a great manager. Every time I tried, I didn't really succeed very well, so I will probably die a developer. I'm a software engineer at Microsoft working on a fabulous product called Kusto. You should check it out. Okay, a horror story. Let's start with a horror story. I love horror stories in 3 parts. Part 1, requirements. Your team lead asked you to build a service, a microservice. It's an image manipulation service. It manipulates a set of images. This is a toy service. It's not really production grade or anything. So you build it. It's a REST API, /flip/ and an image name, and it flips the image. We're going to use Fastify because you're not using Express anymore, right? Anybody using Express? Don't raise your hands. Be ashamed. Thank you. And we're going to use GIMP. It's an image manipulation library. Part 2, the code. This is the code. Well, most of it. We use Fastify. We use the route /flip/file. We read the file using GIMP. This is ESM because, as a lot of you know, I'm an ESM geek. So all of what is in ESM, you don't have _ dir name. You have import.meta.url. Not very important. So we use GIMP to read the file, and this is the manipulation, and this is the important part. I clone the file and then flip. And then I get the buffer. This is async. It's not really async. There's an await there, but I looked at the code. It's totally synchronous. And this code is also synchronous. And we get the buffer and return it to Fastify, which returns it to the client code. Done. Write some tests. Deploy to Kubernetes in production, auto-scale it to handle the load. Auto-scaling is very easy in Kubernetes, and great success, you're done, you go home. Part 3, the horror. A week later, DevOps comes back. What did you do? The dollar amounts we spent $100,000 on your service. What happened? Let's run autocannon on the server. Autocannon is a really nice utility, which I love. And what it does is it runs, you can see autocannon here. You can see autocannon here. I give it the URL, and I tell it to run the server, and it sends lots and lots of requests, and the average request per second is about 5 or 6. It depends on whatever, who knows. So, 6 requests per second, 5, 6 requests per second. Obviously what happened is that autoscale worked and ran it on 25 VMs or whatever to handle the load, and that cost a lot of money. 6 requests per second is not very good in terms of servers. But why did this happen? Why? It's very simple. This line, the file.clone.flip, takes roughly 16 milliseconds on this specific image, whatever. This is GIMP, by the way. It's a really nice library. Please do not use it. It's written in JavaScript. There are better libraries with C++ or WebAssembly or whatever that are much faster. I used it because it's pure JavaScript and it takes a lot of CPU time, and this is what I needed, a lot of CPU time. So let's see why 16 milliseconds of synchronous code is problematic on a server. and this is a story of two requests. The first request comes in to this, and then this is the same code, obviously. The second request comes in, so we now have two requests coming in. JavaScript runtime is basically running the first request, and GIMP is reading the file from the disk. So this await is waiting for the file to be read from the disk. Because there's an await here, the JavaScript event loop can switch to the second request. So now we're switching to the second request. Now this await is awaiting the reading of the file. We can flip back when the first request finishes. Let's say the first request finishes reading the file. We run this line. This line takes 16 milliseconds. Nothing can happen during that time except that synchronous code. JavaScript can't flip to another request when running synchronous code. It just can't because it is single-threaded. So 16 milliseconds waiting, doesn't matter what. Then we get the little await that allows us to flip. Another 16 milliseconds in the second request. This await allows us to flip back. We return the image buffer here. We return the image buffer here. How much time did it take to serve the two requests? Easy. 16 milliseconds plus 16 milliseconds. Synchronous code blocks JavaScript because JavaScript is single-threaded. So six requests, if you do the math, roughly 1 second. Why did this happen? JavaScript is single-threaded, can flip during awaits. Well, this is a simplification of when it can flip, but basically, since we're all using async await, then it can flip basically during an await. If there's no await, it can't flip, so it's stuck for 16 milliseconds. The problem is JavaScript is single-threaded. So, is JavaScript really a toy language? No. Don't believe the rumors. We are multi-threaded. How? Worker threads. JavaScript was single-threaded until web workers came along. Web workers is a standard in JavaScript. It was implemented in browsers around 2012. Came to Node.js in 2019, roughly. Basically the same API. There are various minor differences, but it's basically the same API. And now we're in 2024. We can use it, worker threads, without a problem. Let's look at the code using web workers. Same code. So we create a worker using new worker, easy. Again, we give it a JS file. The JS file is what the worker thread runs. And now it's really running on another thread. So image rotation worker.js, which we'll see in a second, is running on another thread. Now we do flip file. We get the image URL just like the last time, nothing interesting here. But instead of flipping the file, we post a message to the worker. We tell the message here's a job for you. We send the image file URL, and we send a message ID, a random ID. We'll see in a second why we need that. Well, just in a, so we post a message. Now we have to wait for a message to come back from the worker so that we can get the image. So the worker will get the message, process the image, and return a buffer with the message. So we wait for the response message. We'll see the code in a second. Get back the image buffer. Let's look at wait for response message. This is really, really cool. It used to be we did add event listeners and remove event listeners, all this horrible, horrible, horrible stuff. And if we forgot and there was an error, then there's a leak. Really, really horrible stuff. Today, it's really easy to wait. What I do, I use on. This is a new function in Node.js. It comes from the event module. I say on worker. So what it does is wait the on worker comma message, doesn't add event listener on the worker, and waits for that message to happen, and returns it as an async generator, so I can for await it and wait for the message. If the message that I get in the for await is the message with the message ID I'm working for, I can return it. Now notice when I return it, what happens? What happens is the for await knows that I'm leaving the for await, and it removes the event listener from the worker. So the whole add event listener, remove event listener, even if it throws, even if it doesn't throw, just happens automatically. The code is much nicer. This has nothing to do with workers, but please start using code like this, much nicer than add event listener, remove event listener. Okay, and once I get the buffer, boom, I return it, and Fastify returns the buffer. So schematically, how does it work? The worker listens for the job, and we'll see the code of the worker for a second. The main thread posts the job to the worker and listens for the response. Notice this, the line is dashed. Why is the line dashed? Because it's waiting, but asynchronously, so it can now deal with other requests during the time that it's waiting for the response. So it's listening, but asynchronously, while the worker thread synchronously is doing the job and posting the job response. The listening for the response ends, and it can return the image. This is easy. Now let's look at the worker code. First of all, I listen on whatever, it's called the parent port. It's basically listening for worker messages, messages that are posted to the worker, and I get a callback with whatever was sent to the worker in the post message. I do the whole image manipulation, including the part that is synchronous. This is important. Get the buffer and post a message back with the message ID, which we saw how the main thread is listening to the message. Pretty easy. Let's see the results. Oh, 5, same, 6 requests per second. Huh? But we used web workers, right? Why did this happen? Is JavaScript still a toy language? No, let's understand. We have one worker. So we just moved the waiting from the main thread to the worker. The worker is still doing the 16 milliseconds and waiting on it. So we just moved the problem. We didn't solve the problem. Okay? This is like the government does. Sorry. Any government. Okay, what do? We create a thread pool, obviously. And basically, this is what is being done by Java, C#, etc. All those thread-oriented languages, they also have a thread pool. This is not JavaScript specific. Let's create a thread pool. Why does this solve the problem? Because the main thread, when a request comes in, it posts the job and awaits the response. And because it's awaiting, it's asynchronously awaiting, so it can handle other requests. When another request comes in, it posts the jobs to the next thread, etc., etc. And the main thread doesn't get stuck, almost. Why would it get stuck? Because maybe all threads are working at the same time. So let's look at the code. Instead of one worker, I create 4 web workers with the nice trick of array fill, really nice thing. And I create four workers, and I'm good. And I have a pointer, it's an index really, to the array which says what is the next worker for you to use. App-get flip file, we know this, but now I first of all figure out which worker to use. How do I do that? I increment next worker, mod by 4, so that it'll always be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And this is how I get the next worker I want to use. Now I do the regular post message and wait for the message with the worker I chose, and I'm done. Okay, I simplified the code here a little bit. So basically I'm choosing the next worker to use in what is called round robin. Okay? Now, why 4 workers? Why not 10? Why not 20? How many workers do I need? It's pretty easy. If this is a CPU-intensive task, then you should have as many as the number of CPUs you have. How many CPUs do you have? Use os.available parallelism. This will give you basically the number of CPUs. You can also use os.CPUs. On my computer, it gives me the same number, so I'm not exactly sure what is happening here. But if you use that and create a worker pool of that size, you're good to go. Let's run it. And finally, we have a lot more parallelism in our code. Woo! Yes, worker pools. Thank you. The algorithm we used, as I said, is called round robin because it's like a robin, whatever. I have no idea why it's called round robin if I think about it. It's a round something. It's simple to implement. You saw a next worker ++ mod 4. But the algorithm may be choosing the wrong worker because maybe a worker is taking more time and another worker is taking less time. It's not really, it's just choosing a random worker according to the order of the workers. Not very good. A better way would be to know which worker is free, choose a free worker, and use that. Very complicated, unless you use Piscina. If you use Piscina, which is a library that does worker pools for you, you're good to go. So this is the server code with Piscina. I do new Piscina. It creates a worker pool. Instead of doing a post message, I call run on the pool. It chooses the best worker there is, gives it the image URL, and I return the image buffer. The Piscina, I don't need to do post message, listen on message. I just need to export a function. It flips the image, returns the image buffer, and Piscina takes care of all the sorted details of post message and all that. So really nice. There are other libraries, but please don't really create worker pools on your own. Use Piscina. There are other good libraries for it. I use Piscina. All the other examples, I will be using raw worker pools because this is a tutorial and I want to show the sorted details. Next thing, I want to talk about this line. Look at worker.postMessage. I'm sending image file URL and message ID. How is that object passed to the worker thread? Is it passed by reference? So when I post a message, the other thread knows accesses it via reference? Or is it copied? And the answer is, thank you, that is true by copying. The messages are always copied from one to another. And why? Because by design, worker threads don't share memory. This is very, very important. They're more like processes if you understand the difference between threads and processes. If you don't, that's fine. Why call them worker threads if they're not? Because they are implemented via OS threads. The isolation is not via the operating system, but via the JavaScript runtime. And I want to talk about this one, which is really bad. When I post message with the image buffer is copied. So if I have a 1 megabyte buffer, that image buffer is copied, and that takes time. The copying is done by something called the structured clone algorithm. It's used in a new function called structured clone, which knows how to clone objects and everything. But it's a deep clone. It doesn't clone everything. Functions, it doesn't clone URLs, it doesn't clone dates, and it doesn't clone others. But it does clone buffer and array buffer. So we're good there, not a problem. And it's used not only in structured clone, but in post message, the same algorithm. You can find it in MDN. So isn't copying an image wasteful? As I said, it is wasteful. Let's fix that using transfer lists. Remember this worker thread? Remember how wasteful this copying of image buffer is? It's very simple to make it not copy. We just add a transfer list. We tell it, look, you see this image buffer? Don't copy it. Move it. That's it. But it moves the array buffer, but after it moves, after you do the post message, you're not allowed to touch the object anymore because it's not yours. It's the other worker, it's the other thread that has that thing. If you try it, it throws an exception, by the way. Tried it. So that's transferring an image buffer, and we're good to go. There's a small detail. A buffer isn't transferred. A buffer has inside it something called an array buffer, which is the real JavaScript thing that holds the bytes. That is what needs to be transferred. So it has to be image buffer.buffer and not image buffer. If you try image buffer, you'll get thrown. So we said that threads don't share memory unless you use shared array buffer. Oh, makes sense, right? I'll switch to a worker that calculates pi because it's still a CPU-intensive operation, calculating pi. I tried ChatGPT because I had no idea how to calculate pi. I got 4 different results. One of them almost worked. I still have a problem with the last digit of pi, so if you tell me, no, that 100th digit is wrong, yes, I know it's wrong. ChatGPT. Don't trust it, never. Okay, so the worker thread calculates pi and returns a buffer with the digits of pi, 100 digits. But this time we'll use shared memory instead of transfer lists. So the idea is this. The main thread sends a copy of pi result buffer. It's still a copy of the result buffer that the worker thread will insert, but the copy points to the shared memory, points to memory that is shared between the 2 worker threads. Okay? So it's still a copying, but the underlying array buffer is good to go, and it's like really, really shared. So the usual preamble: choose a worker and get the number of digits to calculate. We create a new shared array buffer. The number of digits +2. The +2 is for the 3 dot blah blah blah. Remember, pi starts with 3 dot. Yeah. Okay. And I post a message with the result buffer. I send the shared array buffer to the worker, and I wait for the response. And boom, once I get the response, it's an array buffer. It's a shared array buffer. I can't return it. I have to wrap it with a buffer.from. This is not a copying, this is a wrapping. So this is good. Let's look at the worker. As I get the pi result buffer, that's the buffer that I want to insert the result in. I compute pi. Doesn't really matter how. You can look at it in the GitHub repo. Not very interesting, and there's a bug there. Pi string, I get a string with the digits. Now, I take the shared array buffer. It's a buffer, but I can't access it by itself. I have to view it. It's called viewing. It can't be used as an array. It's called viewing. You create a uint8 array or an int8 array or an int32 array. You create an array of bytes. Uint8 is bytes that view the shared array buffer, and any change on the uint8 array will actually change the buffer. This is how JavaScript works. I have no idea why. Okay, now once we have that as an array, we can use text encoder to encode it into the buffer itself using text encoder, and it encodes UTF-8, but in this case it's ASCII, so not a problem. The digits in the string are now digits in the shared array buffer. And we post a message back with the message ID. I don't need to return the shared array buffer because the main thread already has it, and we're sharing memory this time. Perfect. So we have the shared array buffer. I sent it. The worker thread inserted the result into the pi result buffer, and now I can use it and return the image in the main thread. Very, very nice, and improves the performance a bit. Instead of posting either via transfer list or via copying, which is obviously really bad. Last tool in the tool belt. And maybe I'll have time for one more thing. This is really interesting. I want to get rid of this. I send the job to the worker thread. That makes sense using messages. That makes sense. But why do I have to await that message and read all the messages in the word that the worker sends to me to wait for my message? Isn't there a better way to do that instead of posting a message back? Obviously, there is. We can stop using messages for synchronization. By the way, Piscina doesn't really use messages to return back. It uses this method, which is atomics. And atomics is an interesting thing by itself, and theoretically has nothing to do with worker threads. Okay. This is hairy. So this reminds me of the days when I wrote assembly code. So bear with me. So we have the pi result buffer, which is a shared array buffer, and I'm sending it along with the digits just like the last code that we saw. But I'm also sending another shared array buffer that I call message ACK. ACK as in acknowledge. So this is what we will be using for the thread to notify the main thread, the worker thread, to notify the main thread that I'm done, you can go. This is message ACK. It's a shared array buffer of size 4 bytes. How many ints can a 4 byte hold? 4 bytes is how many ints? 1. Int 32, yes. Okay, and I will use atomics.wait async to wait on this shared array buffer, and we'll see how. So this is the general. So let's look at the server code. As usual, we choose a worker from the worker pool using round robin, create a PyResult buffer with a shared array buffer, just like last time, so that the result will get into this buffer. And then we create an ACK buffer of size 4 for 1 int. And we create it as a new shared array buffer, but we can't insert into the new shared array buffer as it is. We have to wrap it, view it with an int32 array. So we have an int32 array of size 1. And then we set the first element in the array, which is the only element in the array, we set it with a value of 1. Okay? We don't really have to do it. It's mostly for the explanation. That line of setting to 1 isn't really necessary, but it made sense to me for the explanation. And then I post a message. You can see it. I post a message with the message ACK, and we're good. Now I post a message with the message ACK, and I wait for the result not by waiting for a message to come back, but by waiting on that atomic. That array of 1 int is the atomic which I am waiting for. I'm telling it, look, you see this message ACK? Look at the 0th index of that, that's the 0, and wait for it until the value changes from 1. That's weird. Once it changes from 1, the wait async finishes. But it's really weird because look at it. I do a wait async, but I'm not awaiting the wait async. I am not doing that because it may be that the thread has already done its work and the value is ready, and the value of the message ACK is not 1 anymore. So if the wait result is not async, then I have the value. If it is async, I have to await it. This is an optimization that is being done. We'll see it in a second. Once I awaited or not awaited, once the atomics tell me I'm ready, I return the buffer. And it looks like this. Atomics.wait async. So it's waiting until the value changes from 1. If it hasn't changed from 1, it tells me that this is an async call, so I need to await the res.value, and we're good. But maybe the value is already different from 1. Great. Res.value will be not equal, and the atomic has changed, and I don't need to await anything. So in this case, sometimes I don't even need to do an await. The worker code is easy. I compute pi and generate the shared array buffer just like previously. And then I store, using atomics.store, I store a 2, which is different from 1, in the array. And I have to do a notify, I have no idea why, but that is how it is, to notify all the threads about the change. And that is when the other thread gets the notification and wait async exits. That's it. No post message, a lot nicer, not very difficult to implement. So basically, don't post messages back when you're using worker threads, or just use Piscina. Summary. Web workers enable us to run CPU-intensive tasks in our web servers without blocking the main thread. Communication is via post message. Returning a value from the worker thread can be done either via a return post message or atomics and a shared array buffer. And values are copied in messages, always remember that. And if you can also be transferred using a transfer list or using a shared array buffer. I think we're done. Thank you very much.